In this video, I'll be working through the question you see on this screen from the mechanics paper 4.2 from the Cambridge A-level exams from 2023. I'll be doing this on the board, hopefully just like you're used to your teacher doing in a classroom. If you want any other questions from this paper, you should be able to find a link to the playlist in the description below. And if you find any of my videos useful, I'd greatly appreciate if you subscribe, or if you think any of your friends might find it useful, please go ahead and share it. In question 4, they tell us about a runner that weighs 84 kilos and they're running along a straight road and they're going at a speed of 3 meters per second. And they're also telling us they're producing 60 watts of power. Now, I missed something there when I said about their speed. It didn't say they were moving at 3 meters per second. It said they were moving at a constant speed of 3 meters per second. And that word constant is also very important because that tells us there's zero acceleration to this runner. Let's put a dot in as the runner. They then ask us to find the resistive force. So usually if you go running, there's a lot of forces resisting you. The air resistance is a big one, friction on the ground, the inefficiency of your run. Would that be in it? I'm not sure. Anyway, there's lots of things resisting you in this case. So how do you find that? Let's see. This is the big clue here. He's going at constant speed, which means he's not decelerating. Which means he's not, or they're not forcing themselves forward. There should be no force in this system. But he's adding power in, and power does equal force times velocity. So if there's no acceleration, means there's no force, which means there's no power. But there is a power, so something's not quite right here. So what we need to realize is they're putting power in, 60 watts, and they are going 3 meters per second. So really they're adding 20 newtons of force. They're adding 20 newtons of force to this run, to this movement. But it's not working, it's not getting any acceleration. So that means there must be something else taking this force away or working against them. They're working this way, something must be working against it, and that force must be 20, and that's it. That's the answer to part A. 20 newtons. If their force is 20 newtons, the resistive force, resistance force must be 20 newtons. That's it, there's nothing more to really part A. Now part B gets a lot more interesting. The athlete is then running up a hill, a 150 meter long hill. Let's turn this into a triangle because they tell us it has an angle of 0.8. And let's fully turn it into a right angle triangle, much easier to deal with, and it's going to help us later. They start the run, probably the same athlete from the same previous moment. Starts at 3 meters per second. 3 meters per second. There, it also tells us other things. Tells us they have a force of 24 newtons. Again, they're forcing themselves up this hill. They're adding 24 newtons of force to this system. Unlike previous though, the resistive force is 13 newtons. So they're driving themselves up more than they're resisting themselves. That's interesting. That tells us a lot. They basically ask us to use the energy method to find the speed at the top of the hill. Now, use the energy method is important because there is another way to do this. What you could do is you could say, well, force gives me acceleration. You have initial speed. You have distance. You can find acceleration, not just from these two. You need one more thing for the acceleration. But you could find it, and you could do this question, but you'd lose a mark or two. They ask you specifically use energy. The other force you would need, by the way, they're driving themselves up the hill. They're being driven against by air resistance. They their weight is also pushing them down. They'd have get a component going this direction of their weight. So they'd have this plus force, this minus force, and they'd have another minus of, what would that be? That would be, I think, 84 sine? Yeah, sine 0.8 by 10, of course, for gravity. Something like that. Anyway, you could solve that using just forces, find acceleration from this, but that's not what they want. Let's take this plus and minus out. They want us to use the energy method. We're going to still use all the same things. In fact, the same number will appear. The energy method works like this. We look at the energy at the start of the system, everything we know at least, kinetic and potential energy. We look at the energy at the end of the system, kinetic and potential energy, and then we think what added energy in and what took energy away. And we just equate it all out. So in this system, let's say state 1, the start down the bottom of this hill, there's a kinetic energy of a half m, which is 84, a half 84 times 3 squared. And there's no potential energy because they're at the bottom. You get to pick where the bottom of the world is, and they're at the bottom. They're at the lowest point we know of, so we call it zero potential energy. And then state 2, the top of the hill, they're still moving. They tell us they want to find out how fast they're moving, so we assume they're moving. A half 84 v squared. So we don't know the number. Instead of 3 squared, we don't know it. We leave it as v squared. And then they have a potential energy. We just need to know this height. So the potential energy is their weight, their mass, times gravity, times this height. And we can solve this height. That's just trigonometry. Sine of this angle is the opposite of the hypotenuse. So this height would be 150 times sine 0.8, which is very similar to what I had up here for the forces. Although I haven't checked that, but I hope I wasn't wrong with the number I put up there. I just assumed it was the same because this will appear in here. And well, that's it. That's the known energy at the start, the known energy at the end. But the secret is what's added into this system. And we know there's work done here. There's work of 24 newtons times over the whole hill times 150. That work's added into the system. There's more work then. Work of 13 newtons times 150. Now that's not added in. That's actually going to be taken. That's working against them. It's going to slow them down. It's going to take energy away from the system, or it's work done against it. And that's it. There's nothing else doing to the system. His weight of the body is accounted for in the potential energy. So what we can say is, at the start here, let me do it up here. Let's go around that. Need lots of room for this. We'll say this energy, half 84 times 9, plus this energy, 24 times 1 times 150, minus this energy, 13 times 150, must equal this energy, a half 84 phi squared plus 840 times 150 times sine 0.8. Now I just want to point out, you could have saved yourself a little bit of room on these two. 24 going in, 13 coming out of the system. You could have just said 11 was going in. 11 force was going into the system. But still, we can clean this up. This is a long mess, but there's only one thing we don't know, phi squared. You can just solve. Just go ahead and get phi equals out of all of this. I would suggest getting all of this and moving it over this side, putting all that into a calculator, and we'd get a half 84 phi squared is equal, and I put it into a calculator for us, something like 268.765 ... Apologies if this is wrong, I just jotted it down. Again, solve this, divide by 42, I guess. We would get phi squared is equal 6.399 something. Put that into a calculator, square root of that into a calculator, and we get 2.53. What's this? Speed. Meters per second. And that's their speed up the top of the hill. Always ask yourself, does it make sense? Like if you got an answer of 400 meters per second, does it make sense? They're jogging up a hill and they're not going to become the world's fastest runner all of a sudden. If you got an answer of minus something, doesn't make sense. They never would have got to the top of the hill. Ask yourself, does your answer make sense? It looks reasonable. They started at 3 meters per second. At the top of the hill they were going a little slower. That makes sense to me. They were pushing hard. Wind wasn't too bad against them, but gravity hurts and it slowed them down. Okay, I hope that answered this question. If you have any follow-ups, put them in the comments below. I'll do my best to get back to you. Thanks for watching and have a great day.